Our next step is to then start with a simple baseline model. So as I mentioned earlier, often people, they start modeling, they assemble everything they think might be relevant, and they try to do lots of big automated processes to get rid of features and do big grid searches to get the model. And what often happens there is you get a model with a lot of features that are irrelevant. So feature selection is not like a perfect science. It doesn't work that well. And it's costly to have a lot of features in your model. And you don't always want to choose the features that necessarily gave you the absolute best metric, right? Again, I said if you've got 200 features and it gives you one value, and you've got 7 features and it gives you almost the same value, you don't want to pick the 200 feature one, you probably want to pick the 7 feature one. It's costly to have a lot of features in your model. Every feature is a potential failure point. And in many, and probably most cases, you can get most of the performance from relatively few features, and you want to be judicious about what you add into the model to get this performance. So to do this simple baseline feature, I'm going to start with just this simple baseline model. I'm going to start with 5 features based on our exploration. So I'm going to look at the lot area, this overall quality, the year the house was built, the square footage of the house, and the number of bedrooms. So we're going to start there, and we're going to build a random forest model and just use the defaults of this random forest model. And then we're going to just look at things like the mean squared error, the mean absolute error, and the R squared. So we get a mean squared error of 26,327. Often I like to look at the mean absolute error. So we talked about this if you saw the module I did about the metrics for regression. Mean absolute error I think is a little bit more informative. So this tells you on average I am off by 18,590, this model is. So remember our mean value, this is where it helps to have the mean value in your head. The mean value was $184,000. So on average, I'm off by about 10% in this model. So you could say, okay, that seems like a reasonable model. My R squared is 0.874. So this seems to be a perfectly reasonable model. And we can look at a scatter plot just to get a sense. And you see, this looks pretty good, right? Nowhere are we too far out. There's, maybe one outlier over here, but most of the time we're doing a pretty good job. And we don't see any sort of crazy residual patterns or anything. So this took 10 seconds to run, right? And now we have a starting point. Now when I run a model, I know if I'm doing better than these numbers, okay, I've made some improvement. And if I'm doing worse than these numbers, I'm not doing as well as my baseline model, so something is up. And I can judge if I build a model with 200 models and I get a mean squared error of 25,000, I might say, well, that's not that great, because with just 5 variables, I got 26,000. So I did a lot of work and had a lot of variables to get relatively little performance gain. So that's why this is really important. Just to go forward, we could create a second baseline model. Let's do a second baseline model with the full set of 11 features. Again, just as a comparison. And you see, this model now we got to 23,000 in mean squared error, 16,000 in mean absolute error, and R squared of 90%. And compared to the previous predictions, which I recreated over here, you can see, for example, that if I take the mean squared error, the new mean squared error versus the old mean squared error, it's about, I improved it 12% in my root mean squared error. So this looks like it's a pretty substantial improvement, going from the 11 variables, going from the 5 variables to the 11 variables. I had a pretty significant improvement. So again, this is useful because it gives you a sense of what size improvements, when you're able to say, adding this information gave me this much improvement, this starts giving you context for, as you iterate and improve it, how significant your improvement was. and you're able to see, better judge when you're getting, you know, very small marginal improvements, whether those are really meaningful or not. So in this case, I would say our R squared went from 87.3 to 90.2, and we had a 12% drop in root mean squared error. Feel pretty confident that those 6 variables that we added are adding significant predictive power. And we could just again do this plot, look at it again, and you know, just visually you can see it seems a little bit tighter along that line y equals x. Okay, so now we can start. Now that we've built a baseline model that was a simpler method, used a random forest, and we had it for a few simple sets of variables. Now we can start modeling with gradient boosting, and having a baseline will help us determine the quality of our hyperparameter settings, of our feature selections, of all of that. So I want to talk a little bit about XGBoost. So for this, for now, we're going to focus on using XGBoost. There's several really good gradient boosting packages out there. XGBoost is probably still the most popular. And talk a little bit about some of the advances in XGBoost and how it compares to standard gradient boosting that we discussed earlier. So XGBoost first came out in 2015. The acronym was for Extreme Gradient Boosting. And it implemented a number of theoretical and practical improvements. And many of these improvements have now become standard practice in subsequent packages. So I'll talk about them a little bit just to help give you a sense of what made XGBoost sort of stand apart when it came out from the previous gradient boosting packages. So one big thing that XGBoost did was to implement native handling of missing data. So the old gradient boosting, like the standard scikit-learn as it was in 2015, you couldn't have any missing values, so you had to do imputation or something like that. XGBoost said, that's not really necessary. Let's check missing values and let's treat them as if, let's try sending all the missing values to one side and then sending all the missing values to the other side for every cut point. So if I'm looking at a variable and I say I'm going to split this variable at 27, I'm going to try 2 variants. I'm going to try 27 with missing to the left and 27 with missing to the right. And I'll see which one fits better. And so the idea is kind of if missing values really should be a certain equivalent to a certain numerical value, it'll kind of find its way there. And this was a really smart improvement and also really added to the usability of boosting. XGBoost also does Newton steps, so they kind of redid the math, and I'll talk about both the Newton steps and the advanced regularization now. They basically redid the math and incorporated shrinkage similar to lasso and ridge regression into the equation. And so when you're finding the best split, it's already looking at some penalization for model complexity. And it's also doing this sort of Newton step. So a Newton step means rather than just finding the gradient, you actually look at the first and second derivatives and say, assuming that I'm quadratic here, how far would I have to go to hit the minimum? I need to find that as the step size. Something else that XGBoost did, although they didn't, I don't think they realized the significance of it at the time they did it, was to not check every split. So they had a method for, let's say I'm using like income as reported on your tax form as a variable, right? So you've got lots of different unique values, right? Somebody had $63,422 of income. Somebody else had $67,497. Now, you might not need to check every single possible split of those variables, right? You might just want to check it like round numbers or just check a subset, because it's unlikely that when I go from $67,243 to $67,244 that there's going to be some massive change, right? So they basically said, you know what, when we've got a lot of quantiles, when we've got a lot of different values, let's just pick some quantiles and only check the quantiles. They said pick a subset of values to check. Now they did this, the intention of doing this was to speed up the training, because it takes a lot of time to check all these different split points. And if it's not really necessary, you'd like to avoid doing that. Turns out that you also, it's been realized later, you also get better performance sometimes. This serves to regularize, because if you check every single point, you kind of tend to overfit because there's so many little places where you can find some little idiosyncrasy of the data, of the training data, that makes it look like this is a really good split. So it turns out that it's effective both for speeding up the training and as another source of regularization. And the final thing I'll talk about with regards to XGBoost is they did some distributed training. So they created some implementations for working with large data sets that are not in memory. Okay, so now that we've talked a little bit about XGBoost, let's give it a try. So let's define an XGBoost model with the default parameters. So we're not going to specify any hyperparameters. We're going to say, whatever you think are the best set of parameters, I'm just going to do this. Let's fit it. You see it ran pretty quickly. Let's make some predictions, and let's see how they do. So this is on the 11 variable model. Let's compare it to how our random forest did. So we see that we actually, XGBoost, just off the shelf with no parameter set, actually does a little bit worse than our random forest. And this is actually not uncommon because gradient boosting in general does better than random forest, but only if you really get the hyperparameters right. Now, as we'll see, it's not, you don't have to get all the hyperparameters right, you have to get the important ones right. And in this case, we see that just using the default values for the learning rate, the number of trees, and so forth, you're actually doing a little worse than random forest. Now, again, if you didn't do these random forest baseline models, you wouldn't know that. So that's another reason to do these baseline models. So when I do this baseline model, I realize, like, hey, these default settings are not really good. I should not proceed forward experimenting with different features or doing feature engineering and stuff until I get some of these hyperparameters into a good place. Okay. So how are we going to start changing these hyperparameters so that we have a good model? And we just saw that the default parameters on gradient boosting can easily give you results that are not very good. Here it did worse than a simple random forest. But I want to emphasize, this does not mean you have to start doing massive grid searches and go crazy tuning every single variable, every single hyperparameter in your gradient boosting model. So as we discussed in the earlier course, the fundamentals of gradient boosting course, which you may have seen already, the three most important parameters in your boosting model are going to be the max depth, the learning rate, and the number of estimators. And setting these is made more challenging by the fact that they're really interactive. So once I change that learning rate or change that max depth, that's totally going to change what the right number of estimators is. There's going to be almost, once I double the learning rate, I'm going to have a much fewer estimators. As I make the tree deeper, also going to need fewer estimators. So how should we handle this? And the best way to handle this is to set aside what's called a validation set for early stopping and use kind of a comfortably low learning rate. And when we define the model, we'll use a high number of estimators. We're not actually going to build all those trees because the early stopping will tell us. So that's just kind of like an upper limit of how many trees to build. So the way, again, early stopping works is we're going to add a tree to our model, evaluate it on this validation set that's data that's not in the training set, see how it does. And then every time we iterate, we compare whether we got better or worse on this validation set. And at the beginning, we'll be doing better on the validation set, and then at a certain point, we're going to flatten out, maybe start doing worse on the validation set. And then you could use different rules to say, when do I want to sort of call it quits and decide that, hey, I'm not getting any improvement here, let me just stop where I am. So XGBoost makes this easy to implement. So let's try this out. We're going to create a new XGBoost model, call it XGB1, and we're going to now set it up to have 5,000 trees, 5,000 estimators, and a learning rate of 0.01. So the 0.01 is just a comfortably low learning rate that we know won't kind of go too fast. And I don't really expect to use 5,000 trees. 5,000 is just a big number, an upper bound, because what's going to happen is the early stopping is going to kick in. It's going to kick in at a much less than 5,000 trees. And the early stopping will say, hey, I'm not getting any better on the validation set. That means I'm probably starting to overfit. So let's just stop right now. So let's run this. So we define the model. And we're going to add trees. So you see now when I call fit, I give it my X and my Y. I also give it this evaluation set. So in this case, I'm just going to use the test set. Now this is a slight cheat. To be very, very careful, you should really have a completely separate validation set that's different from the training test. But for now, for simplicity, I'm just going to use the test set. There's a slight cheat in that my performance on the test set is going to be a little better than it should be because I picked the exact number of trees that work best for that test set. But I'm also doing the same cheat and the same sort of favoritism for all of my models. So to the extent that I'm just doing this process to see which is the best model, it shouldn't make that much of a difference because I'm letting everybody cheat in the exact same way. Now, if I was trying to, if I was trying to estimate what my performance is going to be on the next set of houses, I'm probably going to be a little bit favorable. So that's why this is a little bit of a cheat, but we're going to kind of ignore that now for simplicity. And this early stopping rounds, I set a 10, and this basically says if I don't hit a new low for 10 trees, so at the beginning I'm improving kind of every tree, so I'm always hitting a new low. Then at a certain point, I don't hit a new low, I'm either the same or a little bit worse. And then, but maybe I get a little worse, but then I get better and I hit a new low again. So then I want to just keep going. And I'm going to stop once, if I've gone 10 rounds and I still haven't hit a new low, then that's when I'm going to stop. So let's let that run now. And you can see this is the validation root mean square error values. And you can see they're getting better, 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 better. Until we get down here. So you can see that over here at 774, I had 22922.51. So that was the lowest so far at that point. And then I got a little worse. And then I kind of stayed at the same level. But I never got better than that value for the next 10 trees. So after I had 10 trees where I was unable to break below that low, it said, hey, I think I've leveled off. I think this is as good as we're going to get. In fact, I think we're going to get worse if we keep going. So let's just stop here. So now we can make the predictions, and now we can look at this performance. And you see now we did better. We did better than both the previous model, where we just used the default settings, and better than the random forest. And again, only a little better than the random forest. But still, at least we kind of know we're on the right track now. Now, that's the first part of the, what I think are the important hyperparameters to tune. First is to use the early stopping. This way you get rid of you don't have to worry about the number of estimators and the learning rate. But we still do have to care about the max depth. The max depth is a really important parameter, and so you do have to tune that. The nice thing is, once you've kind of taken the other two out of the equation, when you only have to tune one variable, it's pretty easy, because it's just you just try a bunch of different values and see which one is the best. Once you get more different things that you're trying to optimize simultaneously, that's when things start sort of exploding in computational complexity. So let's do the max depth tuning now. So I wrote a little for loop here that I basically say we're going to try all the values between, in this case, 1 and 9, because this is Pythonic, so 1 to 10 means stop at 9. And we're basically going to train with that max depth using the early stopping, make our predictions, and look at our root mean squared error. And we're then just going to plot how it changes, how our performance changes with max depth. So this will run for a little bit. It's going to try all the different max depth values. 1, 2. So I'm going to let this run. Okay, so it's gone through all values from 1 through 9. And let's take a look at the plot and get the min. So we're going to plot the max depth versus our root mean square error, and we're going to get the min. So you see that we get the min at max depth of 3, and we get a minimum of 21,631. So let's just train our next XGBoost model. Let's just set it at that depth so that we have this sort of best max depth model. And let's let that run. This runs pretty quickly. And then we're going to look at the predictions. Okay, so after it's finished running, we see that we get, again, this mean squared error of 21,631, which is significantly better than our last model. Our R squared is 91%, 91.4% compared to 90.4%. Our mean absolute error also went down. So we see a pretty significant improvement. Our mean squared error went down by, more than 5%. Just by tuning the max depth. So again, now that we've kind of done the big 3 parameters, the max depth, the number of estimators, and the learning rate, now that we've sort of taken care of all 3 of those, just doing that gives us now the improvement that we expect to see over a random forest. Right? We're at 21,631 compared to 23,000 something for the random forest model. So this is where you see the gains from gradient boosting. And you just have to really get those 3 hyperparameters right to pretty confidently get improvement. Not all the time, but the vast majority of cases, if you tune those 3, you'll already see a pretty significant improvement over the random forest model.